Hello, y'all. Welcome to lesson 80 of my DP chemistry curriculum. Today we're doing reactivity 2.2.1. We're discussing the rate of reaction, which is expressed as the change in concentration of a particular reactant or product per unit time. And we should be able to determine rates of reaction or figure out ways to determine rates of reaction by the end of this, as well as we'll talk a little bit about calculating rates from tangents of graphs. So, what is a rate? A rate, specifically, is the idea of change over time. Change over time. In graphs, we generally think of that as like the slope of a graph, because that would generally show us the change over time of our dependent variable over our independent variable, time usually being our independent variable. But in reactions, what we're really looking at is specifically the change in concentration over our time frame. And we can measure time in seconds, minutes, whatever. Concentration is usually moles per decimeter cubed. Generally, as a reaction proceeds, we see that reactants decrease as they're being used up and products increase as they're being produced. We can measure the rate either way. If you're looking for an actual expression, rate is the change in reactants over the change in time, or the change in products over the change in time. Again, we're using delta to represent change. Now, we are also using our square brackets to represent concentration. Remember that square brackets mean concentration. And so these will be opposite values. The rate and the reactants and the products will change in an opposite rate. And we can calculate that as well. But for now, what we're going to talk about are different techniques to identify the change in rate. So that's what we're going to mostly focus on. Whoops. Techniques to monitor changes in rate. So we're going to go through each one that might appear on the DP exam or you might use in a real lab. And I'll try and provide a little commentary on which ones are most commonly used in different scenarios. So one of the best quantitative methods we can use is change in volume of gas produced. So we often see this when we're looking at reactions. For example, a metal plus acid. This usually produces hydrogen gas. And we can collect that in a gas syringe. Collect in gas syringe. And generally your experiment might look like this. You have your Erlenmeyer flask and you have your acid, maybe HCl, and you have some zinc metal solid in here. And what happens is it produces hydrogen gas, which we can put a stopper and attach it to a syringe, specifically what's called a gas syringe. And these have very low friction. And so that as you are collecting gas, the plunger moves back, and on our gas syringes, so that's our gas syringe. On a gas syringe, what you'll generally notice is that with the plunger, you have markings of volume. So you have 0, then maybe 10, and it's etched onto the gas syringe. So you can calculate the volume, and usually it's going to be in centimeters cubed. So as your H2 gas fills that, your hydrogen gas fills it, you can monitor that. And you just take the volumes at certain times. So you can create a simple table of like time 0, volume 0, time 10 seconds, volume centimeters cubed. At 10, maybe you have 5 centimeters cubed. At 20, you maybe have 7 centimeters cubed. At 30, you maybe have 8 centimeters cubed. And generally, as reactions progress, they slow down as reactants are being used up. So you might end up even creating a graph of this data showing how time changes 10, 20, 30 with volume 5, 7, and 8. And so you get a nice little graph that looks a little bit like this. And so you can use the volume of gas produced in any reaction that produces a gas, collecting with a gas syringe. And this is one of the most common ways that I've seen in labs, I've used in labs, and I've seen appear on the DP exam as a way to actually monitor the progressive rate of a reaction, as well as get quantitative data, so numerical data that gives you an identifier of rate. All right, we're going to move to probably one of the least common methods I've seen, which is change in mass. And again, this might be in a gas production. So when a reaction releases gas, you can kind of just let it go and see the mass change. And you can do this on a scale and measure the mass before or after, or measure it taking place over time. But something you have to account for is if you are doing a reaction that produces hydrogen gas, as that gas leaves, it's going to be filled in by air, which air has a heavier mass than hydrogen gas. So you're going to have to take into account the difference in masses. Meanwhile, if you have a reaction like baking soda and vinegar, you might release carbon dioxide, which will then get replaced by air. And on average, carbon dioxide has a heavier mass than air. So there's these factors that you have to start thinking about as you do a equation by mass if you are taking that overall volume. It's a little different if you're producing the gas, you're filling the chamber first, because what you may realize is, well, normally there is air. As the reaction proceeds, it gets replaced with H2, which is going to make it appear lighter. And then as the H2 leaves, then it's going to get heavier again. So you're going to get these fluctuations. This will help you kind of determine the rate of the reaction by monitoring changes in mass. But getting qualitative or quantitative data is often quite difficult. So with that, we'll move on to another qualitative experiment you can do, which is change in color. This can be qualitative or quantitative, but we'll talk about both methods. So some reactions change in color. This is very common. They can also create colored solutions. This is very common when you're using things like, this happens with indicators, which you generally use monitoring acid-base reactions. It may happen when you're using transition metals. Transition metals are often colored. For example, like copper will be bluish in water, but if you start removing copper from that solution, the color will start to fade. So it happens quite often where we have colored solutions. The issue is that if we want to do it, if we want to create a quantitative data set, we need tools. What you generally use is a colorimeter, which will fire a wavelength through your solution of a color, and that wavelength of light will pass through or not, and it will be read on a sensor, which gives an absorbance value to know how much light was absorbed based on the color of your solution. And so what you can do is you can create what's called a calibration curve. where you make set solutions of specific concentrations. So concentration 1, concentration 2, concentration 3, and you plot that concentration versus absorbance. And as you get that graph, when you get your new solution, you can calculate the absorbance and use that to figure out what your concentration is. So generally when you're doing a quantitative data set from a color change, you'll need to start using tools like a colorimeter and maybe a calibration curve to actually identify what your rate is. Instead of just general fast or slow, you'll need some type of tool to measure that. All right, another one that we can do that also requires a tool is going to be, whoops, let's keep my formatting, change in conductivity. Solutions with a lot of ions are more conductive, so either the reactant or products have different ratios of ions. And therefore, as we produce more or less, we can see a change in conductivity. It's usually helpful here to do an example. So if we look at CH3 CBr, so we take like a trimethyl or bromotrimethyl methane, and oh, that is not right. Sorry, a bromomethyl propane, whatever, and we take that and we react it with water. What we will often see is that water will be split and we will get CH3COH and we'll get an alcohol group here, which will create an H plus ion in solution, aqueous, and a bromide ion in solution, aqueous. And now we go from originally 0 ions to 2 ions or 2 moles of ions. And what this means is as we start creating more products, we have more conductivity. So we'll notice the conductivity increase as this reaction progresses. We can then plot that on a graph of time versus conductivity, and we'll notice it going up as we create more products. And so we can measure rate that way as well, because that conductivity relates to our creation or concentration of products. So that is another quantitative way. One that's often done in early experiments is the rate of formation of a precipitate. A solution might get cloudy as we form a solid. So forming a precipitate is solid. So that's forming a solid in an aqueous solution. And so generally what you'll see in experiment is you'll have an Erlenmeyer flask. And under the Erlenmeyer flask, you will put it on top of a paper with like an X. And as you have your solution, you can normally see through it in a colorless solution. However, once the reaction starts, duplicate that one, and a precipitate is formed, so you'll notice the solutions start to become cloudy. Let's pick a different color here. Let's pick a yellow. And the solution will start to get a little bit cloudy. And the cloudier it gets, the more the solution, so solution becomes cloudy, the more the solution becomes more opaque, and you can no longer see that X that was once there. And what you can do is actually just use a stopwatch. Here's me trying to draw a stopwatch, and you can time how long it takes to go from being able to see the x to not being able to see the x anymore if you want to get some quantitative data as opposed to this qualitative data right here. In terms of using stopwatches, the other type of reaction we can do is measuring a clock reaction. You may have seen these online. Generally, one of the great examples right here is an iodine clock. That's the solution that just suddenly turns black out of nowhere. And what this actually is just a rapid color change. So this is once again a color change reaction, but it's a rapid color change which occurs after a delay. And that would be due to a mixture of reactants. Generally, you have like maybe a slow reaction, which leads into a fast reaction. And this fast reaction is where the color change occurs. And what we're really doing is measuring the slow reaction by timing it. So we time until the fast reaction. And that gives us a rate on that slow reaction. We can change factors like concentration or temperature, and we can see how much that slow reaction changes its rate based on the time it takes to get to that fast reaction. So these are the many different ways we can actually measure rate of a reaction. But what do we do when we use a quantitative method and we have data? So what we generally do is we graph quantitative rate data. So what we can generally do is we create a graph that has, oh, no, we'll just do basic lines. Generally, it's time because we're doing reactions. So we're going to do concentration of products. We could also do concentration of reactants. And I will do two different graphs for that. For products, I'll do that in purple. You might have a graph that looks like this. Maybe you have a graph, I'm going to do two for products that looks like this. Here we have our slow reaction, and here we have our fast reaction. Reactants, you'll actually notice a slightly different graph. It generally starts from the top because we start with reactants and we end with products. We're going to have inverse graphs, and we'll also do a slower reaction. So here our red is our slower reaction and our blue is our fast reaction. It's not so fast. I'm going to redo our blue one just to really speed it up. Oh, one more time just to get it right. There we go. So the steeper that initial line, generally the faster we believe that reaction to be and the faster that reaction is. So we can identify these reactions as being fast or slow, but we have data, and because we have data, we're going to try and get actual calculations. So there are three types of calculations we can do. Calculations of rate from graphs. So the first type we can do is what's called an instantaneous rate. And that is the rate taken at any point in time. We calculate an instantaneous rate by drawing a tangent line. Drawing tangent line to a graph at the desired time. Whoops. Desired time. And then with that tangent line, we then just calculate slope. The DP exam loves making students do instantaneous rates. The other one they really love to have students do is what's called the initial rate. Initial rate is the same thing as an instantaneous rate, except for this is time equals 0. So you are basically still doing an instantaneous rate at time equals 0. So it's exactly the same steps. You're still going to draw a tangent line to the graph and then calculate the slope. It's just if it's at time equals 0, we call it an initial rate because it is the initial rate of reaction. The last kind of rate calculation we can do is the average rate. The average rate is very much as it sounds. It is the slope calculated between 2 points on the graph. And it would therefore give you the average rate between those 2 points in time. So what we can do really quickly is a practice problem on this. So I'm going to draw a graph right here, and we'll try and make it very proper. We'll have our title. Today we'll do volume gas produced. So I'm actually using a volume of gas produced instead of a concentration because what we're going to get is a decimeter cubed or I should do or centimeters cubed over time. And so instead of a concentration over time, we're getting a volume over time. And that is completely acceptable. I know we went through the whole thing and we discussed all of this as concentration over time, but it is just acceptable if you're doing a gas production to do volume over time. If you want to calculate concentration, you can kind of reverse engineer it, but volume over time is a completely acceptable form of rate that I did not put in our previous ones. So we'll say volume hydrogen gas produced. We'll say it's in centimeters cubed. And here we'll do time, and we'll say it's in minutes. We can do pretty much anything we want with that, but we'll create a nice little graph. You'll notice the slope starts steep as we have a lot of reactants and smooths out as our reactants decrease. So we'll just put some initial data points here. Let's just say I want to make our math easy as we do this. We finish at about 10. So 10 minutes, and we'll say that our maximum volume produced is 20 centimeters cubed. All right. We'll look for an instantaneous rate, maybe right in the middle, smack dab in the middle at 5 minutes. And we'll start adding some more points as we see fit. And we'll try and keep them pretty straightforward. So we can calculate all our different points. So we'll start out with initial rate. So for our initial rate calculation, what we will do is create our tangent line. So that's the line that is tangent to our initial point or our initial part of the graph. When you take the DP exam, what you're going to want to do is actually bring a ruler with you so that you can start making these tangent lines. I guarantee it will be part of it. And it looks like we're going to need a time here. So we're intersecting 20, so we can use that. And we might say this is at 3 minutes. So for our initial rate calculation, for our initial rate calculation, we're going to just calculate the slope of our line. So at 20 minus 0, so that's our volume, our max volume minus our minimum volume. We're doing rise over run, so this is a slope. So our high slope value minus our low slope value. And we will divide that by 3 minus 0. Our large time value minus our small time value. We're taking this point divided or subtracted from this point, and that is our slope calculation. You should be pretty apt at calculating slope. That's going to be 20 over 3. And when you plug that into your calculator, you will get a value of, now I have to plug that in, 6.66 infinite, so we'll say 6.7 centimeters cubed per minute. You know what? We'll use DP language, minute inverse. Next, we will do our instantaneous rate. Instantaneous rate. And we're going to do at time equals 5. So what we're going to do is once again create a tangent line. And we're going to need some new values here. We'll say this intersect is about 7. And we'll say this intersect is about 15. In a DP world, they're going to give you graphs that fit pretty nicely, so you don't have any doubt. So we'll do our 20 minus 15 divided by 7 minus 3. That's going to be equal to 5 over 4, which is going to be equal to 1.25, or I've been using 2 stick figs, so I'll say 1.3 centimeters cubed per minute, or minute inverse. You'll notice the slope, the rate of our initial versus our instantaneous has decreased dramatically. Lastly, we will end with our average rate. And this will be over our entire thing from T0 all the way to 10 minutes. So we'll do 20 minus 0 divided by 10 minus 0. We'll get 20 over 10 for a rate of 2 centimeters cubed minute inverse. And for that, we don't need a slope. We literally are just calculating this line right here. So I hope this helps you understand a little bit about the rate process, calculating rate, and pretty much dealing with any of these measurement techniques, analytical techniques, and yeah, all of that. Hope this helps and have a great night.